So I think we're just waiting on the slides to go up right now. Awesome. You guys able to see all that? Fine. It's a little bit small, but. And then let's see if I can figure out how to advance the slides. Does the button work or? Sorry, technical difficulty. Perfect, perfect. Awesome. Well, thanks everyone for coming out today. Really appreciate it. So what I'm going to be talking a little bit about today is DNSSEC and how CloudFlare is sort of implementing that within our own system. Now you'll notice there's a couple people that are mentioned here. So I'm actually speaking on behalf of the engineers that actually designed this system. But I'm really excited to be here with you guys today. So at CloudFlare, when we sort of came up with the idea of doing DNSSEC within our system, we had two primary goals in order to do this at web scale. One was to make this a highly scalable system, and two, to make it incredibly simple to use. So the maxim that we worked on was that DNSSEC shouldn't only be for power users, it should be for everyone. And when we had to do this, in order to reach those two goals, because we have such a large deployment, in order to accomplish that, we actually had to do two primary things, which was writing our own DNSSEC system. In order to reach the scale goal, this was just necessary. And in terms of reading the simplicity goal, we actually are proposing a modification and extending of existing protocols to sort of automate registrar interactions. Now, when I say like a large-scale DNSSEC deployment, I want to sort of set the stage to how big that actually means. So with CloudFlare right now, we actually have 2 million domains on our system. We're authoritative for about 40% of the Alexa top 1 million websites. And we serve about 43 billion DNS queries per day, which is second to only about VeriSign. And also when I talk about scale and size, it's not just the amount of requests and how big our server deployment is, it's also how geographically distributed it is. So currently this is this is the most recent network map I have right now. Unfortunately, we open up a new data center about once a week. So this is even a little bit out of date, but we have 43 data centers globally distributed all over the world right now. So let's talk about scale. So when we approached the idea of doing DNSSEC at the edge and at this scale, we came to the conclusion that live signing was really the only way in order to do this. This was necessitated by the fact that we have those 2 million domains in our system, and when you have 2 million domains, not all of them are getting requests all the time. A lot of these will be very light traffic zones, and we're having to distribute all of these zones across all of the 43 data centers, which means that we need to have essentially dynamically generated records. And then of course we need to deal with the problem of zone walking protection. Now, with every solution, of course, comes its own challenges, right? And so the three challenges in terms of scale that we ran into were speed, negative answers, and key management. And then we also put some constraints on ourselves when we were designing the system, which was keeping the record size as small and no longer dealing with the idea of having full zone files for every single domain. All right, let's talk about the fun part. Are the solutions we came up to deal with these challenges. First one, speed. Oh, actually, let's take a step back real quick and talk about an overview of what CloudFlare's DNS or DNSSEC system looks like. So we actually have our own in-house DNS server called RRDNS that's written in Go. We did this because we needed our DNS servers to be resilient against attacks and abuse. We couldn't have zone files anymore, so we actually have a globally distributed database with all these records in them. And we needed to have the DNS server be fully featured, right? So dynamic answers, CNAME flattening, etc. And DNSSEC just becomes another one of those features, and actually is a filter that can be applied to any answer that our DNS servers serve out. Now, solving the speed equation, and actually consequently size as well. the way that we went about this was essentially using modern cryptography, right? So elliptic curve cryptography versus RSA. And even without any performance improvements, we were seeing that signing operations were happening about 3 times faster with elliptic curve signatures versus RSA. Now, one of my colleagues, Vlad Krasnov, actually took the OpenSSL ASM and ported it to Go, and in doing that, introduced quite a few performance improvements. So now we're seeing a much faster signature operation, 21x what we were before. And then we actually got some bonuses out of this too. Because we switched over elliptic curve, now we're seeing much smaller signatures, much smaller keys. And also many of the validators out there, all except for one when we first started this project, supported this already. And then the last one signed on pretty quickly after we started working with this. The next sort of step in that process is working with the registrars to get them supporting this as well, which we've had some good progress with, but there's still a little bit more work to go on that one. Here's a quick example of sort of the difference in size you'll see between RSA and elliptic curve signatures. We do this just to be very illustrative about what that looks like. And in terms of like absolute numbers, this is what we're seeing in terms of the signature operation. I highly recommend that you read the blog post that we did on this. It goes into a lot more detail about how exactly Vlad came up with these performance improvements, but obviously a little too much to go into for this presentation. All right, so the next thing we're going to talk about is negative answers and how we solve that. So normally when you think about DNS and you have to return an answer that says a record doesn't exist, we're thinking about regular NX domain records, and when you apply DNSSEC to them, there's some unfortunate consequences we have to deal with. We have database lookups for previous NX names, 2 or even 3 signatures depending on whether you're doing NSEC or NSEC3, which can get very slow and very big. And then of course the security concern around disclosures of the previous NX names. And this is a quick example of what that looks like, and you can see there that we're actually moving up into upwards of 700 plus bytes just to respond back to this one query. Now, the community actually addressed this, or tried to address this through RFC 4470, which introduced white lies for online signing. And the idea was basically generate an NSEC record on the name's immediate predecessor, cover up the successor, which of course can be applied to both regular NX domain and wildcard requests. And then the big thing that this is solving is actually zone walking and those database lookups. But we're still running into the issue where we have 2 signatures just to say one thing. So we thought, what ways can we improve on this? So our solution was actually just to create true lies. So in the case of CloudFlare, we're actually just signing a no error record and then placing the NSEC name on it, again covering the successor, and in this case only setting the NSEC and RR sig bits. And here's a quick example of that right there. Now you can see the benefit we're getting out of this right now. We're actually seeing the response bytes in the 300 range right now, like not pushing over into a 700 plus. And the big benefits we're getting out of this is now we only have a single signature operation, no database lookup, no more zone walking, and the entire answer can actually fit into a standard UDP packet instead of having to cross over into multiple. And I think the big win on this one is that end user behavior is actually unchanged. But there was one other issue we had to deal with when dealing with negative answers, and that's to deal with when a record exists, but the type they ask for doesn't, right? And typically in the past with DNS servers, you would get a response back that would tell you, this record doesn't exist, but or this record does exist, but not that type, but all of these other types do exist. The issue is that when you're doing this with dynamic answers, that's not always possible or becomes very, very expensive, right? So when we approached this problem, we actually took a step back and we thought about what exactly is NSEC. It's just a denial of existence, right? These types in the bitmap don't exist. So instead of trying to both say this doesn't exist and these ones do exist, we tried to create a minimally covering case where we set all other possible bits in the bitmap. So here's an example real quick of a TXT record that doesn't exist, And so all we're doing is saying the TXT record definitely does not exist, but any of these other records could potentially exist. And we got some benefits in terms of attackers and how they would use that to replay for other queries. So the final point I'm going to talk about in terms of scaling is going to be key management. Now, when you're running this highly distributed system, you're actually going to run into some problems with having centralized DNS key sets. And when you're live signing, you're still going to need the zone signing keys at the edge. Now, that's a problem for the present. We're actually hoping to solve that problem in the future, but that's sort of a completely different talk. So in this scenario, we can still protect the key signing key and keeping it safe in a central auditable machine and distribute the signed DNS key sets to the edge. And this allows us to do a couple of things. We can have short, regular RSIG validity and slightly longer TTLs for DNS keys. But the big thing we have to keep in mind when doing this is we always have to be prepared to roll the ZSK fast, essentially at any time. Now, normally when you think about DNS and DNSSEC, you think about having different keys essentially for every zone within it. Now, when you have millions of zones, that becomes much less tenable. And actually, when we thought about it, we realized that there's some strong benefits to only having a single zone signing key and single key signing key. And this is that if there is ever a reason to roll it, there's no more looking for what needs to be rolled or figuring out how big the breach is. It's more of just roll everything because it needs to be rolled. And you can see the example right here of multiple different domains on our system essentially having the same DNS key record. Okay, so that first part was more thinking about how you deal with scale for a DNSSEC system of this large. This next section is going to be talking about how to make this simple and consumable for customers all over the world. Now, at CloudFlare, we are huge fans of the internet. We live and breathe this. And because of the ubiquity of the internet, we've all sort of become to expect that internet, things on the internet happen very, very quickly, right? Things happen in seconds rather than in hours or days. But I think we all know, if we've been working with DNS for a long time, that DNS propagation delays can actually force us to be thinking about things in like days or multiple days in order to make changes. A recent example of someone who got bit by this was actually HBOnow.com. They recently started making some changes with their DNS servers and they kind of forgot that they had DNSSEC enabled on it. So a lot of the DNSSEC enabled resolvers started failing when they started making changes. Now this caused a lot of issues for their customers, right? Because they're not able to resolve this anymore. And even after HBO was able to make changes to fix this, it still took upwards of a day in order to purge all of the DS records from the resolver caches. So in this scenario, things aren't really happening at internet speed anymore. So before I go into like how we're looking to solve that, I want to take a step back and talk about the registration model in general and where providers like CloudFlare sit in this. So CloudFlare is actually a third-party DNS operator. That definition is basically an entity contracted by the owner of the domain to operate DNS on their behalf. This includes like CDNs, DNS specialists, appliance vendors, even just friends of friends. And millions of domains are actually operated by these third-party DNS providers, and many important domains sit on these as well. Now, if we look back and we look at the registry model and how it was originally conceived, we can see that we have all the different parties in here, but one that's conspicuously missing from there is mentions of any third-party DNS operators. Yeah. So when we're thinking about reforming that model, we have to think about what exactly the third-party operators actually want to be able to maintain. And it's really only three things, right? It's the NS records, the DS records, and the A/Quad A records. And have a way so that the parent and the child servers can always be in sync. So in today's world, what happens is the registrant always has to be involved in order to talk with the parent. The issues of this, of course, that it's not particularly very reliable. It's up to human intervention, not necessarily timely, and you can have human error in there. The way that people have dealt with this sometimes, and we don't particularly love that, is that they'll just give access to the registration accounts to the third-party DNS providers, which is not particularly a great solution for security's sake. Another potential solution for this is actually if third-party DNS providers became registrars, which addresses part of the problem, but there's bigger issues with doing something like that. It's actually really very difficult to become a registrar in all ccTLDs, and usually these third-party DNS providers and registrars have business relationships that make things a little bit more complicated. So let's think about what exactly the third-party DNS providers want specifically. It's really just two things. The ability to gain authenticated permission to maintain delegation information for our customers, and the ability to learn where to change and connect to that system to make those changes. So let's take a look at this from the perspective of DNSSEC, right? In this scenario, we have a child zone that can actually advertise what the contents of the name server and DS records should be. And this can be done via NS records, CDS records, CDNS key records when DNSSEC is present. What we're working on right now is to find a way to actually tell the parent that these changes have been made and to tell them to make the changes on their side immediately, right? That's how we get to internet speed. So if, in the scenario, the third-party DNS gets authenticated and authorized to make changes on behalf of the registrant, then they'll be able to make changes to NS, DS, glue records for specific domains, and then we can actually inject what the correct answer should be into the registration system. And now updates can happen much quicker. And to do that, what we're proposing essentially is we want these changes to happen in less than 4 hours, essentially. And this assumes that changes at the parent can take about less than an hour. And the operations that need to take place, essentially, we have to provision a new operator, change the NS record in parent and the old operator if possible, and then wait for resolvers to expire this out of cache. And the big precondition here is that child and parent NS records have to have a TTL of less than 2 hours, which I think we all realize is not particularly the case right now. And the reason for this, like the reason why we're pushing this so hard, is because DNSSEC KSK rollovers can now happen in 6 hours ideally, maybe even faster if we're hoping for the best, but 6 hours at the least, right? So we're still assuming that changes in the TLDs take less than an hour, and now the operations are update the DNS key or DS records, switch the KSK, purge out the old DS and DNS key records. But of course, this means that child DNS key records have a TTL less than an hour, and child and parent NS and DS have a TTL of less than 2 hours. So given all this, what we're actually asking for is a call to action at this point. And that's to start a discussion on what the right goals and policies are. Now, obviously, we're proposing to get TLDs to adopt lower TTLs, somewhere in the less than or equal to 2 hour range, and then find a way to give access for managed DNS providers to access and maintain that delegation information. And then, of course, a bonus goal of ours is to get registry and registrars to support new DNSSEC algorithms, particularly algorithm 13, so we can get the benefits of the ECDSA speeds that we were talking about earlier in the presentation. So I know that was a lot of information, but I hope you found it informative. I really appreciate everyone coming out here and letting us sort of talk about what CloudFlare is doing with DNSSEC and what we sort of see the future as. Thanks very much.
Thank you. Any questions for Jono from the audience? No one? Okay, thanks, Jono. So the next speaker is Zhang Zaifeng, and he'll be talking of the abuse of DNS wildcards in China from a passive DNS perspective. Zhang.
Okay, thank you. My English is not so good. I will try my best. My name is Zhang Zaifeng, pronounced in Chinese pronunciation. I'm from Network Security Lab at Qihoo 360. Today I will give you an introduction about our database passiveDNS.cn. and from our database give the scale of the DNS wildcards abuse in China. Today's presentation composed 4 parts. First, some information about passiveDNS.cn, and then I give what is the DNS wildcard and how it operates, how DWA operates. At last, I will give some methods about measuring its scale in China. Okay, we are collecting 10% of DNS traffic in China, and it's about 900,000 DNS queries per second. Last year, we have collected 5.7 billion DNS sites and 17.2 billion R dates. It's about 4.6 billion unique domains. I think our database is the first and largest public node passive DNS database in China, and it has open to security communities, include NSPSEC and Ops Trust. From Wikipedia, wildcard DNS record is a record in a DNS zone that matches request for non-existent domain names. A wildcard DNS record is specified by using an asterisk as the leftmost label of a domain name. For example, if a domain is configured with a wildcard record, it's like this, asterisk.example.com in a 1.2.3.4. Any subdomains for zone example will be point to 1.2.3.4. Okay. We judge DNS wildcard abuse. In fact, there is a dedicated name in Chinese. It's Fan Zhan Qun. We judge if a domain is abused or not, mainly from its behavior and its content. Someone registered lots of domains. All these domains have wildcard record enabled. Most of the for qualified domain name web page has duplicated or non-sensible contents, and most pages linked or cross-refer each other. As a purpose, it's a type of black hat SEO, and possibly it's a trick to evade firewall blocking rules. I will explain it later. Let's check some examples. The domain style, they are like the domain style. They are like DJ, but you will never find corresponding NX domains. They had random prefix subdomains. In this page, it's many domains versus single IP addresses. This page, many subdomains versus, many subdomains versus multiple IP addresses. And this page, new GTLD.sense also involves. Okay, what's the real web page looks like? The following pages show 3 different sites with similar page structure, layout, and the content. Check it. Site 1, Site 2, and Site 3. All of them, all pages have some shot of medical rewards, photo of a middle-aged doctor, and nice hospital facilities. If we check the web page's HTML code, we can find some slogans of DWA software provider. Here it shows the ultimate killer team for medical DWA with its website and customer service QQ number. And here is another slogan, the newest ranking technology which current searching engine blocking. Okay, but how it operates, generally speaking, it includes 4 steps. Prepare domain and the VPS, pick up keywords for searching engine, generate fake original content, which to be used by searching engine, and the last step, site goes live. Only first step related with domains. So we split the first step into 4 sub-steps. Purchase domains, purchase VPS, domains goes live, and the last one, generate subdomains. Let's check it separately. Okay, purchase domains. Someone purchase domains from almighty Taobao.com. When you buy Microsoft domains, they are so cheap. Okay, like domain, same as domain. Purchase VPS also from Taobao.com. There are so many dedicated VPS for DWA. Please note the red color Chinese characters. All of these are used. All of these are dedicated VPS for DWA. The industry chain is full blown. Okay. Now we have loads of domains and corresponding VPS. Resolving them are time-consuming and very boring. But don't worry, there are tools to help us and make things easier. I selected one software which named 黑侠战群. You can put your domains on the leftmost input box, and your IP addresses of VPS in this box. Please note the red arrow here. Asterisk resolve. If you select this checkbox and press start adding, later all of your domains will be added with wildcard records. Okay. The last step is generate subdomains. Use the same tool, we can automatically generating kinds of subdomains according to your configurations. Here, there are 2 type pages: the random prefix, the random subdomains and the pinyin subdomains. In these random subdomains, you can configure the length of the subdomains. Also you can use digit only, alphabet only, or mix of them to generate all kinds of subdomains. Okay, when you press this button, start generating all kinds of subdomains. All kinds of domains are generated here. Okay, here only one type of DWA. I think it's not. It's the second DWA, some like domain shadowing in a way. Okay, it's someone intrude the registrants and modify the DNS records. Oh, sorry. Most of the victims of this type are government sites. You know, Gov.cn is used by Chinese governments. Okay, why government sites are mainly targets? I think 2 reasons. The first one is many governments are poor managed. Attack the registrant accounts are easy. The second reason is government sites in some searching engines are ranking here. I think the second reason is the main reason. This method has 2 advantages. Its economy. First one is its economy. You don't need to purchase lots of domains. The second one, same as this. Many searching engines ranking government sites are here. Also, it has some disadvantages. Sorry. It's high risk. It's a criminal. You don't want to get got. Okay, we measure DWA. First select the date and verify it. We select the domains using following rules. First, domain registered in China, but server IPs are located overseas. All of the domains has wildcard records, and the domains must not be. I'm sorry. It's gone. Must not be CDN domains, dynamic domains, and popular domains, and not special IPs such as single IPs and domain parking or reselling IPs. And there are some other filters. Okay, we select 1 week date from 2000 May 15 to 2000 May 21. The total about 948,000 domains, but there are only 35,000 domains are valid. These sites live with web title. I analyzed the content of these pages. The classification result is 45% of them are pornographic sites, 15% are gumbo sites, 9% are misconfigurations of DWA, 8% are normal businesses, 7% are traffic directing systems, and the others about 16%. Okay, let's see the detailed statistics. Okay, from active domains daily, second level domain view. There are no obvious trends here, but here are some 0 points because of some unexpected reasons. No date import our system, so you can ignore them. Okay, we zoom in the ac.cn sense and the gov.cn curve. ac.cn is used for academic institutes in China. It is registered by anybody and no limitations. The average number is 646 per day. gov.cn is an index which reflects the security of government sites. From this picture, we can see there are about 47 per day. The sense number, the sense.sense is a new TLD, which registered which registered at 2040 October. We first seen this at 2050 April 3 here, and burst after 2 weeks it began burst. The highest point is 2050 June 18, and as average number 377 per day. If we check the active domains from 4 qualified domain name, the number is much larger, about 40 times to 18.6 times than SLD. But here is the spike. What's wrong this day? Okay, we check the days of that. We check the date of that day. There are about 50 SLDs which has a large number of subdomains. They had the same style, just like the following. I think it's a testing. Someone who buy the DWA, they are testing. Okay. What about the other new GTLDs? We state the new top 10 new GTLD from 2015 July 7 to August 26. The top new GTLD, the top is a thoroughly applicated area. Okay, here is active server IPs trends. Compared with the domain names, they are stable, about 15,000 per day. Okay, the IP distribution, 83% located in US, 30% located in Hong Kong, Japan, and Taiwan. US is the most matured market of information industry. Hong Kong, Japan, and Taiwan are near Chinese mainland in geographical. Top 10 AS number include 68% of the server IPs, 8 of them located in US, 2 of them located in Hong Kong. Okay, the lifetime distribution. Most of them, 86% of qualified domain name less than 1 day, and 42% SLD's life less than one day. Okay. The domain access count distribution, 60% of the SLD DNS request less than 1,000, 88% of the SLD DNS request less than 500. You know the time span is about 7 months. 500 DNS request is really scarce. Okay, the conclusion. The DWA is very popular. About 2% of the new emerged domains belong it. But as you check from the DNS request number and the domain lifetime, I think it works not so good. This can be verified from another DWA software. Its slogan side, the only effective DWA software out of the web. But why it's so big still? Some reasons, I think, not every webmaster knows this conclusion. Most of them are still spend lots of money to buy this software and produce so many rubbish content and rubbish sites on the internet every day. And not all of the DWA used for SEO. Some it's a type of domain flux. It's used for evade the firewall, IPS, or WAF's blocking policy. Okay, that's all. Thank you.
Any questions for Zhang? All right, so the next speaker is Elise Gerich, and she'll talk about the DNS root zone KSK rollover.
Is it this one? Thanks. Hi, I'm Elise Gerich from ICANN, and it's quite a pleasure to be sharing the stage with my 3 esteemed presenters. You can kind of consider this a little intermission, my presentation. I'm really substituting for Ed Lewis. I think many of you know Ed. And he told me that I'm really supposed to be just the opening act for Geoff Huston. So I have a very short presentation, and then I will turn it over to Geoff. So basically, whoops, I went too far. 3 topics, so I'll be pretty quick. This is all about the DNSSEC signing of the root. So where are we today? We signed it a while ago. What about rolling the root zone KSK? And then how do we get to a plan to do that so we don't break everything? So today, basically, we signed the root about 5 years ago. And when I say we, what I'm talking about are the 3 root zone partners. That was ICANN, VeriSign, and the Department of Commerce from the US government, NTIA, because they had the contract that told VeriSign and ICANN that we should sign the root. I know the community wanted that to happen also, but it really did happen under the auspices of that contract. So after that, everyone said, okay, well, should we see what happens in a disaster? Should we try rolling the root? So what we've done is we put together a design team to look at what we should consider. And I think, do you pronounce your name Jono?
Yes.
Jono talked about some things that maybe we should consider, so I hope CloudFlare will consider sending us some comments in our public comment. So the design team members that were selected from the community are listed on the big screen behind me, so I won't read all their names. One of them's sitting on the panel right here, and so I'm sure he's going to give you some insights into what the design team's been talking about. And the design team also includes the technical staff from VeriSign and ICANN and a representative from NTIA. So I won't go into great detail about what is the KSK, stands for Key Signing Key, just in case you didn't know. And they're basically a pair of keys. There's the public key and then the private key, which is only kept inside the hardware security module called an HSM. And what the design team's been looking into are, what would the impact of a key rollover have and what things would need to be updated everywhere. So the planning approach has been that this current design team has for several months now had regular phone calls, an enormous number of email threads, different discussions. They've come up with a draft and they've put it out for public comment. As you know, we've talked about several different public comments that are going on right now from an ICANN perspective. One of them's the IANA Stewardship Transition public comment from the ICG. There's the accountability public comment from the CCWG. And we also have a DNSSEC key rollover public comment. This public comment is set to expire September 15th, so you have a little more time than some of the others. And we really are looking for community input, especially from those of you who have rolled the key for your TLDs perhaps, or from those of you that are vendors and have some feelings about this, or if you're researchers and you think you have some great ideas. So once the public comments are in, about a month after that, the group plans to put together their final report, which again will be a plan of what would be a proposal for a DNSSEC key rollover. So what I'm here today to say is send feedback. And you can send it to the URL that's up on the screen behind me. I think the slide deck is also posted. You can reach out to the design team members and share comments with them directly. There are a couple around here this week. And you can also come up to the microphone for the Q&A after Geoff's presentation, and then we can answer some questions then. But that's my brief intermission between my 3 esteemed colleagues' more in-depth presentations about DNS and DNSSEC, and I'll now ask our moderator to come up and introduce Geoff, unless he wants me to introduce him. I guess Geoff's going to introduce himself. Thanks very much.
Thanks, Elise. Thanks, Elise. So this is now part 2 of this. The DNS is a miracle, isn't it? It's a miracle because every single thing you do requires a DNS transaction. So these 3 billion odd users of the internet pummel the DNS daily. And quite frankly, it's a miracle it works. But even more astounding there was this work done by CloudFlare. 20 times faster using ECDSA. That's amazing. and the response of a signed response under 512K. Amazing. I am astounded at this. Astonishing work. So what we're going to do is bugger it all up and break it. Why is this important? Oddly enough, DNSSEC is actually way more pervasive than IPv6 in today's internet. After a minor glitch in the last couple of weeks, who's here from Telekomunikasi Indonesia PT? Anybody? Maybe they're fixing DNSSEC because they stopped validating last week. Naughty. But a lot of the world validates. 14% of the world actually looks at the signed DNS answers, and if they don't like it, won't go there. That's amazing. Even more amazing is that in Southeast Asia, it's higher than the world average. It's one of the few things that this region of the world absolutely leads. And if you look at the map of the world, in Vietnam, in Malaysia, and bits of Indonesia, there's a lot of DNSSEC validation actually going on. So oddly enough, this area of the world has really picked it up. 1 in 6 users of this region will not go to a site if its DNSSEC validation is broken. If it's badly signed, they won't go there. That's amazing. The V6 folk could kill for these numbers, by the way. They would literally kill. So this is an astonishing number. So why is this relevant? Because quite frankly, we're going to bugger it up. We're going to completely break it, because what we're going to do is change that key signing key. Now, the zone was originally signed 5 years ago, and the commitment was made 5 years ago in this document, and I've pulled it out for you at your leisure, and there's this little bit circled that says, in 5 years' time, we're going to change the key. And that was 5 years ago. So, it's time. So what are we talking about? As you've heard twice already, so maybe you'll remember, there are 2 keys working around this place. There's the working key, the zone signing key. Every time a new root zone is created, and it happens about once a day, they pull out the zone signing key, which is near line, and use it to sign the new zone, and then sign it again and again and again every day. They roll that key regularly. VeriSign look after this, and it's rolled every quarter. Now, all of those zone signing keys that they use have been signed at the back end by a single key, the key signing key, the KSK. This is hardly ever bought out. And when it is bought out, it's in this ceremony with people with funny hats and video cameras and all kinds of wacko things. I think they're the new Shriners of the internet age. And they go out and do this strange song and dance and sign a whole bunch of ZSKs, right? The reason why it's important is that if you're validating, and 1 in 6 of you are, your resolver has a copy of that KSK. And if we go and change it, and you don't keep up, you have a problem. So this key signing key is indeed the key of the DNS. This is it. There's nothing above it. If this gets stuffed up, we've all got a problem. So the key signing key is actually kept in highly secure facilities. And here's a picture of a highly secure facility. It's got floodlights, it's got guards out the front. It's a typical piece of American engineering. It's just brilliant. Over on the west coast of America is the second repository. They're a little bit more relaxed out there in California.
Don't believe them.
And we've been looking, and we found the ultra-secret third KSK repository down in Amsterdam. Dig here. But then we've sent George Michelson off to Uruguay, and he's found the mobile KSK somewhere in the streets of Montevideo. So, there are lots of them around. You've seen this. This is the cast of actors who are playing with this key, and I'm part of that external design team. And we've been working at this for about 3 odd years. There was public consultation in 2012, engineering studies. Even the Security and Stability Advisory Committee had a shot at this in 2013, and the design team's been working this year. God, this thing has bounce, doesn't it? So we've been doing lots of work, doing phone calls at midnight. So if Ed Lewis, if you're listening to this, For Christ's sake, midnight's a horrible hour of the day. Make them earlier. So we're now at the public comment period, final report in September, and then the design team's work will finish and we'll throw it over to the root zone management folk to go implement. But there are some problems. Because as I said, this is the key. This is the key of the entire DNS. So if we go and change it, and you're not following, every bit of signed DNS will look bad to you because you're using an old key. And that could have a really bad impact. So rolling keys is easy, yes? Who of you have rolled keys? Oh Christ, everybody, yes? Almost all keys roll sooner or later. No key is eternal. It's just a prime number. The more you use it, basically the way the security theology works is the more insecure it becomes, you should roll it. So the way you do it's pretty simple normally. You generate a new key, you use the old key to sign the new key to tell everyone it's good, you retire the old key and flip to the new key. Yep. And then if you really want to be good about it, you just revoke the old key to say that's gone, that's dusted. It will never, ever, 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 ever get used again. We're beyond that, right? So just to show you how good we are, yep, here's a colour graph of how it all happens. Yep, it's got lots of colours, so it must be true. There's one critical bit right in the middle of this, at the end of the first quarter, because we publish the new key saying, everyone, you have about 2 months, learn this new value. And then on one day, and it better not be a Sunday, on one day, at one time, and it better not be a midnight, hint, hint.
We're hoping you'll be asleep.
We're hoping all of you will be asleep and not notice. At that point, the new zone file that gets published will have no reference to the old key signing key. You will have had to have picked up the new one, or the entire root zone will look rubbish to you. So that's the critical switch point. And then the next plan is, another quarter later, we'll revoke the old key, there's no going back. So we've done this before. The good folk at the RIPE NCC used to roll their key every 6 months. And the funny thing was, every time they rolled their key, because they were signing the reverse zone, the amount of query traffic went up by a factor of 10. 10. Next 6 months later, it went up by another factor of 10. And it kept on doing this. And we started to look at this and found, oddly enough, that the folk who write DNS resolvers are a very strange breed of obsessive compulsives. Now, most of us in this room are obsessive compulsives. Otherwise, you wouldn't be doing networking and computing, right? So that's a given. But the folk who write DNS are even worse than the rest of you because they were weird. What they didn't believe was what they saw. And so whenever they got an answer, they couldn't validate it. They started aggressively questioning all other ways of potentially validating that signature. So when they saw something they couldn't validate, instead of backing away going, okay, fine, I'm going to go away, that's a disaster, they start pumping more traffic in going, if I ask enough questions, will the answer change? Which was a disaster. So we sort of thought about this a little bit, and actually out came Mike St. John's with this RFC 5011, that said, here's a way to roll the keys that doesn't sort of court disaster. And so this will all work, right? We all support new software. Everyone keeps their DNS software up to date all the time, don't you? And this will all work, won't it? No, I'm like, that's just being hopelessly optimistic. It's not going to work like that, unfortunately. Because when most of you get a DNS resolver running, you go, God, that was hard. Let me seal the box up, put it in a dark closet where no one's ever going to look at it ever again and just leave it running. Because it was so damn difficult, I'm never going to do it again. So we have an awful lot of really, really, really old resolvers out there asking really stupid DNS questions. And some of them, oddly enough, although they're quite old, do DNSSEC validation. And we're kind of concerned about those ones. If they don't do 5011 properly, they're in deep, deep trouble. Now, the problem is that we don't know how many such resolvers exist that aren't actually keeping their eye on the ball. You might know, it might be your resolver, but it's really hard for us to test whether you can pick up a rolling route. Because you're not allowed to do a fake route. I'm not allowed to play with your reality. The only way we can test this is by doing it for real. And if you're not there, you might die, right? So we're really not sure what's going on if you don't support 5011, and that's a given. So this is hard. We can't test it. We suspect it's a small number. We dearly hope it's a small number, but we just don't know. The other thing we're going to do is to up the response time, the response size. What's the largest packet that will always make it through the v4 internet? How many octets? Any bids? God. Okay, I'll give you the answer. You're just not participating, are you? 512 octets. 512. Not even 1500. So you can do a standards compliant implementation of TCP/IP, and if you get an IP packet bigger than 512 octets, you can throw it out and that'll be just fine. You haven't broken any standards whatsoever. Now, the problem is some of you have IP stacks that get not quite close to 512, but you start getting pretty small. And during this rollover, we're going to get a little bit bigger. In fact, at one point, we're going to go over the other magic number. What's the largest packet that a v6 implementation must accept? Must accept without fragmentation? Someone shouted out 1280, didn't you? Thank you very much. It's 1280, and we're going to break that. For a period of a few weeks, we're going to go over 1280. Yeah, stuff it, fragmentation will just work, won't it? Does fragmentation work in v6? And the answer is, well, kinda and kinda not. Because the way v6 does fragmentation is different to the way v4 does fragmentation. That's a problem. So that little area there where we do big answers, just not happy with that. But that's something we can test. Because at Apnic we've been looking at this and we've actually started measuring some stuff, and we're pretty interested actually in what happens when you start to get big DNS responses. Do people still pick it up? So we did an ad campaign to try and do that, and also look at exactly what kind of options are flying around in the DNS itself. So firstly, we'd like to try what happens when we get the response just close to the Ethernet limit. What happens with a response that's 1,440 octets in length? In theory, in today's network, 1,500 octets is the universal size. It's just Ethernet size. Everything supports 1,500 octets. Remco, everything supports 1,500 octets. Well, exactly. Some folk doubt this, and I do too, so we'd like to test that. And the other thing that's kind of interesting, you heard about ICDSA. This is an amazing algorithm. It moves away from prime number cryptography and moves to elliptical curves. It gives you, according to the cryptologists, around 10 times the cryptographic strength for about a third or less of the number of bits. Why are we still using prime numbers when we can go on to something a whole lot better? So the next question is, if we used ICDSA, a new piece of cryptography, how many folk will actually pick it up and use it? How many of you are using cryptography libraries that actually support elliptical curve cryptography? All of you? You're lying. Only some of you, but we'd like to know what that number is. So, the first kind of strange thing about the DNS is that although around about 14-15% of the world do validation, 83% of users request signatures in DNS responses. So all of you are doing 90% of the lifting. So if I sign a zone, most of you will ask for that signature. Whether you validate it or not doesn't matter. Almost all of you ask for the full box and dice. So when the root zone is signed, almost all of you are picking up all of those SIGs all of the time, even if you don't validate it. That's interesting. That's very, very high. The other thing that also happens with a new version of DNS is that we actually have this new signaling. Even though the the maximum packet that you must accept is 512 octets, you can put in a special signal in your DNS query that says, give me bigger, I can take it. And there's a thing called an eDNS0 buffer size. The standard says, for no particular reason, put the value 4096 in there. And that's what most folk do. But some folk are inventive, and instead of using what comes out of the box, they start inventing their own values. And interestingly, people choose all kinds of wacko values, and just there, around 1440, we find around 5.5% of DNS resolvers use a really weird 1425 octet eDNS0 size. I have no idea what drugs they took that morning, but they must have been great, because that's some kind of altered reality that I can't figure out. What does this mean? If you've got a response that's bigger than that, I can't give it to you in UDP. I'll have to back off and use TCP. And you might not like DNS over TCP. So, what did we find when we actually did an experiment to start looking at this stuff? 1440 octets kind of works kind of most of the time. We did 6.5 million experiments and found that around 500,000 timed out, and we found only 47 that just absolutely failed. So most of you, around most of the internet, don't mind a big-ish packet. Just to test the theory, we banged it over that 1500 octet limit. Now, you either had to do TCP or you had to do UDP fragmentation. And 5,000 of you found that was just too much. The magic combination just didn't work. That when you had 1770 octets of payload, 5,000 folk failed. Remember that number. I'm going to come back to it. What about cryptography? ECDSA versus RSA? Geez, well again, we tested this. We actually had a zone sign with each protocol and we looked at it. Interestingly, ECDSA also failed badly. It had around 5,000 failures out of 9 million tests. That's kind of curious. That's kind of curious because the spec says when you get an answer signed in an unknown algorithm, an unknown crypto algorithm, just treat it as unsigned and press it on. But you know, the DNS is endlessly inventive and people who write DNS code are also endlessly inventive, and there's some really wacko code out there. So, not good. That's larger than the RSA failure rate. You know how we do all this work in happy eyeballs, prefer 6 when you can, all that kind of stuff? You remember that? Yes, of course you remember that. What about the DNS? If I hand you a name server that can respond in both 4 and 6, what does your DNS resolver do? Certainly doesn't do 6. Because what we saw is that around the 109,000 resolvers that we actually observed doing these queries, only 2,000 of them were willing to actually do the question in 6. That's really, really small. So what it appears is that in a dual stack environment, 1% of the queries and 3% of the resolvers are actually running on 6. So at any time in the near future, if because of this v4 address shortage stuff, you know, we ran out, you're thinking of going, oh, I'll just set up my DNS over v6. Bad idea. The rest of the world has to get with the plot because we are not in a position to support v6 only DNS servers yet. That number is just disgustingly small. So, you know, there you go. This thing bounces a lot. So some observations. Rolling the root key is big. It's really big because there's an awful lot of folk who pick up DNSSEC and an awful lot of folk who validate. So if we get it wrong, we will break the internet, promise. We will break it. So this is kind of this stuff about getting really close to the edge of the cliff. We'll know when we've gone over because all of us will be falling, right? Not just a small number, a lot. So yes, there's a lot of DNSSEC validation going on out there. That's the first issue. The second one, whatever v6 transitional sending the message out was going on, the DNS folk weren't listening, were not listening. There is remarkably little v6 in the DNS, and it certainly seems from these measurements, haven't looked at the code, from the measurements, Browsers will support v6 in a dual stack environment. Resolvers, the few that do v6, prefer v4. So whatever the v6 message was going out there in the world in general, the DNS folk were in another room and the door was locked. They weren't listening to you. Oops. Some more observations. CloudFlare is sort of right. Sort of right, sort of most of the time. But 20% of the folk who do prime number validation, RSA, do not do elliptical curve. And the reason why is actually all about intellectual property rights. And some folk somewhere in the US claimed at one point in time that they owned elliptical curves. God knows how. And a whole bunch of folk doing OpenSSL software kits decided that they would disable ECDSA by default. And so it was there, but not turned on. Now, eventually all that IPR nonsense got sorted out, and these days we believe that ECDSA is free of that. But there's still this echo of folk being suspicious of using this particular algorithm due to intellectual property. And so that's why there's still 1 in 5 folk who do RSA but do not do ECDSA. And that probably needs to get a bit better. However, the good news is it's a soft failure. Instead of going, oh, I don't understand the crypto, it's obviously lying to me, that's a bad answer, when they see a Cloudflare name, when they see a Cloudflare ECDSA signed answer, they simply go, wow, that's a mystery to me, it must be good. Credible ignorance, love it. So there's no real damage going on there, it's just we could be better. Big DNS responses. Remember I said there were 5,000 resolvers out there that didn't like a big DNSSEC answer. Anyone looked at .org? Anyone here from .org? When you look at .org and pull down .org and look for its signing keys, its DNS keys, the answer is 1,650 octets. So whatever problem we're going to get into with a large DNS response, .org has been there. And if you can't get to a .org name, maybe that's your problem. Because certainly .org is busy doing really, really big answers, and we certainly haven't heard anyone scream about it, so it mustn't be that bad. I don't know how many people are going to do the automated RFC 5011 take-up. Nobody knows. We won't tell till we'll do it. We suspect it'll be small. We hope it'll be small. Can't tell. We're only going to see it by failure. So, where are we? This will cause some degree of failure. Damage will happen. It will cause damage because they won't pick up the new key, and it will cause damage because some folk don't like big answers. Some of you will just switch to using another resolver. You'll use all 8s. You'll go back to Google, whatever. And that's probably a wise thing to do. But a small number of you will find that on that day, Sunday, midnight, whenever it happens, the internet will simply turn off for you. Until you change your DNS, it won't turn on. So here's that URL again, public comment. My date's the 15th of September, Elise. You said the 9th or something, but yeah, 15th, we're in agreement then. Write in some comments from the 15th. Please read and comment. And that was it. Any questions? Because I have some that you should have asked. So, thank you for the question. Why now? It's actually a really good question. Why now? Like we said 5 years ago that we'd roll it in 5 years, but why? We've used it 10 times, twice a year, isn't it? So it's been brought out to light, dusted off 10 times and been put back in the vault. 4 times a year, so we've used it 40 times. The ZSK gets used a whole lot more than that. I don't think the bits are in danger. The bits are just fine. So the next kind of question is, okay, we said 5 years, but what's the imperative? And I suppose the real answer is, we can't delay this indefinitely, and we said we were going to do it, so maybe we should. But if we find a good reason to delay, let's delay.
So one answer is
Oh, okay.
That's one answer that people...
DNSSEC will get bigger, says Elise, and certainly she's right, and we all believe that in the coming months, instead of 14% of the world and a small percentage of the zones, DNSSEC will just keep on getting used. And that's a really good thing. DNSSEC is brilliant. If we roll now, the damage will be a lot smaller than when we roll in the future. So perhaps there is an issue of getting some experience while it's still sort of small is kind of better than waiting until we're all using it. But anyway, why now is a good question. What measurements are planned during that key roll process? Oh, good, it's really difficult. I don't know if any of you have looked at these 13 separate root server operator systems, and they all have their own rather strange rules and so on. Getting open public metrics in the root system is really quite difficult. And so this whole issue around measurements and thresholds. If too many people die, can we back off? When's the point at which we put up our hands going, oops, didn't mean it, roll everything back, let's try again a bit later when we understand some more. Before we revoke, you can roll it back. That revocation is the ultimate, that was it. But before that, theoretically, you can take a jump backwards. But it's kind of an interesting question, and when you read the report, think about this question and think about whether the report answers it, because it's a really interesting question. There's probably more to do there. I find this one, I must admit, this is a question of mine a bit strange. Why do we stick to a calendar? I don't know, are many of you in operations? Do you remember the Christmas shutdowns, the this shutdown, the that shutdown? Because quite frankly, when very few ops folk are around, it's probably a good idea not to muck around with the network. And at the moment, the document kind of points to the fact that when the first of the month of that first of the quarter comes around, we'll just roll the key. As I said, even if it's a Sunday, even if it's New Year's Day, when that date comes, they're just going to roll the key. That just strikes me as a bit strange myself, but you know, you might be perfectly okay with getting woken up at 2 a.m. I'm not. Testing for RFC 5011. This is the one reason why you might want a delay. Because if we had a bit more time, maybe we could do a bit better. Because there certainly are some interesting issues here about a really, really difficult problem. Could we do sentinels? Could we phase stuff in? Could we actually take a more tentative step in the water rather than just diving in and going, that's it, it's the first of the month, new key, if you're dead, you're dead, if you're alive, good on you. Are there ways to kind of test the water a bit first? This is something where I must admit more work and more brain power is needed. So if you have some comments about this in particular, we'd appreciate it. Why are we introducing only one new KSK? Hell, let's introduce 5. Let's line them up. Because if you're going to do all this work, it seems sort of a bit weird not to do a bit more just in case, I would have thought. So serialisation, why wouldn't we sign a few more? And this is this whole thing about, does everyone have to do everything all at once? Would we make the world more confusing if we did one root server at a time, or would we make the world a little easier to back out? What's the engineering trade-off between everyone all at once versus one at a time? Is that reasoning solid operationally? Good question. I'm not sure what the answer is. That's the last slide from me. So that's sort of, I suppose, to give you a feeling of the kinds of things we're talking about in the design team and the kinds of things we are playing with. And I suppose I use the word playing in kind of a light-hearted sense. We are fully aware that the root key of the DNS is incredibly important. And we're equally aware that as we move into all kinds of strange mucking around with IP addresses because we've run out, the only consistent glue that actually holds the internet together is the DNS. And if we get the DNS wrong, you haven't got an internet anymore. And so we're acutely aware that we've got to do this right, we've got to do it well. We can't hang on forever, but we really would appreciate your wisdom and insight from operating your little part of the DNS and how you think that might relate to these plans to go and roll the route. So certainly if you've got any questions now, I'll be happy to field them and pass them over to Elise. Or are we doing such a brilliant job it's all okay? Wow, off free. Thank you very much.
All right, so thanks once again to all of our speakers. So can we have a big round of applause for all of them once again? Wonderful. So this concludes the Apops 2 plenary, and so there is an opening social today in the evening at 7 at the Lobo restaurant downstairs, level 1. So see you all of you guys there, and enjoy the rest of your Apnic 40. Thank you very much.